Hello everyone. This video introduces Oran-Twin X, a sub-project within the Cheddar Hub. In the next 5 minutes, I'll walk through the system architecture and key capabilities. Oran-Twin X is a collaboration project among 4 universities, which are University of Surrey, Leeds, York, and Birmingham City University. Oran is characterized by open, disaggregated RAN components and standardized interfaces, which enable multi-vendor interoperability and more flexible RAN control. Reinforcement learning is widely used in Oran for control and optimization. But its black box nature makes it harder to improve system transparency and trust, so xAI has become an active research direction. In our Oran scenario, the system has 2 key components, the near real-time RIC and the non-real-time RIC, which serve multiple mobile users. To train AI models and avoid real-life overhead, we formulate a Python-based simulation in the digital twin. The collected data is then used to train multi-agent RL offline. Once trained, multi-agent RL is connected to real-life Oran for fine-tuning. The real-life data is transmitted to digital twin via E2 and A1 interface. In parallel, we enable continual xAI to interpret and track the evolving, multi-agent RL policy during online adaptation. At last, we use LLM to help us with visualization. The Oran scenario covers an area of 1,500 meters times 1,500 meters. There are in total 9 cells. In each cell, there are 15 users. In total, there are roughly 135 users. The user mobility is set to be 1 meter per second. From the framework, we could see the handover happened in a certain time step, along with average load among the scenarios. There are 2 agents in our multi-agent reinforcement learning framework. Meanwhile, there are 2 xApps in the near real-time RIC. The first xApp manages power scale, while the second controls the fairness scheduler. The second xApp has 4 levels, where 0 being the most conservative, while 3 being the most aggressive. 2 RL agents operate in a coordinated manner, so they won't fight each other for resource. Once RL converged, the framework could show the mode for power scale, fairness scheduler, HOL delay, average SINR, outage ratio, and reward. After RL made decision, we used a special model called Liner Model U-Tree as xAI. It will explain why RL made the decision for how much power scale and fairness. For visualization platform, we build a self-made Python dashboard. First we could see the Oran system performance. We could see the overall throughput for all users, along with HOL delay, outage ratio, average SINR, and queuing ratio. Then for the RL, we could see the power scale value at real time, and cumulative mode for the second xApp from the visualization. Mode 1 is the most popular mode for the certain scenario. Then, the xAI performance is measured by 3 KPIs. Coverage measures how much decision has been explained by xAI. Precision measure the accuracy of explanation. Stability measures would xAI change its explanation based on the same RL decision. Also, xAI could demonstrate the top rules for each xApp. For example, if the Q ratio is less than 2%, xApp could turn on power saving. In our self-made Python platform, you can follow each scene and see how the boosting ensemble updates, specifically, how the number of trees increases to capture new regimes. At the same time, the LMUT view highlights the currently active leaf and its decision path, showing exactly which rule is triggered and which xApp action it leads to. To sum up, we propose and demonstrate a xAI framework for RL and a visualization platform. This framework could add transparency to Oran key thresholds, enabling more efficient and thorough management. In the future, leveraging the framework, we could enable human interactive management with the help of LLM. Thank you for your time. If you have any comments or inquiries, please find us using the websites on the scene.